So what is electric current? Electric current is the rate of charge flow. So electric current is something that happens when I have charge moving through a conductor or whatever. Whenever I've got charge moving, I've got an electric current. So current is equal to charge passing by a given point divided by how long it took that charge to pass by that given point. It's given by the symbol I, and the unit, of course, SI units, what's charge? Coulombs. What's time? Seconds. So we got coulomb per second. 1 coulomb per second is called 1 ampere or amp. All right. So the current gives the number of coulombs of charge passing a given point in 1 second. So if, for example, my current is 3 amps, then that means that every second, 3 coulombs of charge pass by my given point. All right. There's a convention that essentially everybody uses for current, and that is that current is taken to be in the direction of positive charge flow. Now, we use this convention despite the fact that in almost every situation, electrons are usually going the other way. But it's kind of easier for us to talk about positive quantum. All right, so potential difference is what causes current to flow. If I've got a high potential over here and a low potential over here, then my current is going to go this way because positive charge wants to go away from the high potential and towards the low potential. So that's the way that we can make current flow, is we can make one side of a conductor at a high potential and the other side at a low potential. So we always flow from high to low. What is a magnetic field? Well, a magnetic field is a vector field, and that's this kind of mathy concept, which basically just says that you've got a vector at each point. And this vector field is associated with forces. It's just like the electric field. Remember that an electric field always points in the direction that the force on a positive charge would point in if you put that positive charge somewhere. Magnetic fields are a little bit different. They're a little more complicated as far as their relationship to the actual force. But you can still think of magnetic fields as associated with a force. They don't point in the same direction, but they're associated with a force. All right, magnetic fields are generated by permanent magnets, which are also called hard ferromagnetic materials. The word ferro is similar to the word ferrous, which is associated with iron. So ferromagnets are associated with iron, even though iron itself is not a hard ferromagnet. You can't make a magnet just out of iron, at least not at ordinary temperatures. But there are other hard ferromagnetic materials that do generate magnetic fields. Now, magnetic materials have 2 poles. These are kind of like electric charges, but they're not the same. So, just like electric field lines go out of positive charges and end at negative charges, magnetic field lines come out of north poles and go into south poles. However, very, very, very important distinction, probably the most important distinction between magnetic fields and electric fields. Electric fields are created at positive charge, and they are destroyed at negative charge. It is not that way with magnetic fields. Magnetic fields don't ever start or stop anywhere. They always make closed loops. Always, 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 always. So let's see what that means about the magnetic field line diagram associated with a simple permanent magnet. All right, so we've got our north pole, we've got our south pole. We've got magnetic field lines coming out of the north pole, so they're coming out, and then they go in to the south pole. Great. So now, how do I connect these lines? Well, these North Pole lines are going to come around, and just like with electric fields, they're going to spread out when there's room to do so. And when they're close together, that represents a stronger magnetic field. So we've got it coming around like this, and we've got it coming around like this. So that's our magnetic field. Notice that the magnetic field is strongest at the poles, and then down here, it's not that strong. But now what happens inside the magnet? This is where the difference is between electric fields and magnetic fields. Inside the magnetic fields continue all the way through, just like this.